We share
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Subscribe to our channel. Title of the paper:
Analysis of active and passive control of nanoparticles in viscoelastic nanomaterial inspired by activation energy and chemical reaction.
Author of the paper. Details of the paper. Before we present the theoretical review, let us consider a preliminary introduction.
Active control has occurred when the nanoparticle volume concentration at the wall is a constant property and the haphazard motion of tiny or nanoparticles is dependent on such a constant and wall temperature.
According to some scholars, active control of the optical and electronic properties of nanoparticles is achievable through electronic, chemical, and electrochemical approaches.
The same dimensional governing equation for modeling the mass diffusion convection process where Schmidt number play a major role was modified by changing the concentration to nanoparticle volume fraction by some scholars to explain the passive control of nanoparticles at the surface.
In this case of revised Chen-Minkowitz problem, Lewis number is more appropriate than Schmidt number. It is worth remarking that Brownian motion and thermophoresis parameters play a significant role to quantify the passive control of nanoparticles.
In a published meta-analysis on the transport phenomena of various fluids conveying tiny or nanoparticles, it was concluded that increasing haphazard motion of tiny or nano-sized particles is capable to cause an increase in the internal pressure on the tiny or nanoparticles as discovered by some scholars.
Another meta-analysis on the effects of thermophoresis shows that different responses to the force of a temperature gradient are sufficient enough to enhance the temperature distribution due to an increase in thermophoresis.
In the case of passive control, nanoparticle volume concentration at the wall is substantially influenced by the associated pressure with haphazard motion and associated temperature gradient with the thermomigration of tiny/nanoparticles. In such a case, the Brownian motion parameter is dependent on an infinitesimal nanoparticle volume concentration. Moreover, temperature distributions may be sufficiently declined.
It was once concluded at the end of a study to determine the influence of active and passive controls of nanoparticles on the dynamics of stagnant Maxwell fluid that temperature distributions when there exists passive control of nanoparticles at the wall are lower than when replaced with the active control. More so, the Brownian parameter has a negligible effect on the heat transfer when nanoparticles at the wall are passively controlled. Next, we shall now present the theoretical review.
The dynamics of chemically reactive viscoelastic on a convectively heated surface due to stretching when there are thermal radiation, haphazard motion, and thermomigration of tiny particles was investigated with emphasis to compare the case of active control of nanoparticles and passive control.
It is worth remarking that the dimensionless governing equations of the transport phenomenon are suitable to explore: a. Increasing thermal radiation, b. Increasing haphazard motion of colloidal tiny particles, and c. Increasing thermomigration of the dispersed tiny particles.
Next is to present the empirical review. The analysis shows that for an active control case, increasing the haphazard motion of tiny particles causes heat transfer to decline at the rate of -0.047357692 but enhances mass transfer at the rate of 0.097530769.
Two further exploration using the slope of the linear regression through the data points show that growth in the haphazard motion of tiny particles has no significant effect on the heat transfer for the passive case but causes a rise in the mass transfer at the rate of 0.211168462 for the same passive case.
3. For active and passive cases, heat and mass transfer decreases with higher thermomigration of tiny particles. It is worth remarking that there exists a minima rate of the mass transfer due to increasing thermomigration of tiny particles in the case of passive.
4. However, The optimal rate of heat transfer is seen in the case of passive due to increasing thermal migration of tiny particles. Acknowledgements.
Special thanks to all the editors and reviewers of Physica A, Statistical Mechanics and its applications, Elsevier Publishing. We share appreciates the contribution of the authors to the body of knowledge.